The most expensive building ever constructed for commercial purposes isn't a skyscraper, a casino, or an oil refinery. It's a factory the size of a city block that manufactures objects smaller than a wavelength of visible light. And if you want to build one yourself, not own shares in one, not partner with one, actually build a competitive leading edge semiconductor fabrication plant from scratch, you are looking at a minimum of $20 billion in capital, 5 years of construction before your first product ships, a supply chain that bottlenecks through a single Dutch company with a waiting list, and a Taiwanese competitor who holds 90% of the market you're trying to enter. Here's what that actually costs. Most people think of chip manufacturing the way they think of circuit boards. Something electronic, something assembled, something that happens in a factory that looks roughly like other factories. Wrong. A leading edge semiconductor fabrication plant, the kind that makes the chips inside an Nvidia H100 GPU or an Apple A series processor, doesn't resemble any other industrial building on Earth. The air inside must be cleaner than a hospital operating room by a factor of 1,000. The floors must be isolated from vibration to tolerances measured in nanometers. The water used in production must be so chemically pure that standard municipal water quality classifications don't have a category for it. And the machinery doing the actual work is, without exaggeration, the single most complex manufactured object in human history. That last point is the thread you need to hold on to, because it explains why this industry has the shape it does, why only 3 companies on the entire planet operate at the leading edge, and why no amount of money alone can build you a competitive factory from scratch. Let's start at the beginning, with the ground itself. Site selection for a leading edge fab isn't a real estate decision. It's a geological and infrastructural exercise that can take years before a single permit is filed. The site needs 100 to 200 acres of land with bedrock stable enough to anchor a foundation that must eliminate vibration from nearby traffic, weather events, and low-level seismic activity, because the equipment inside is sensitive to disturbances measured in fractions of a nanometer. The power infrastructure must deliver between 100 and 200 megawatts of continuous electricity, roughly equivalent to powering a small city, with redundancy systems sophisticated enough to prevent any interruption longer than milliseconds, because a voltage event that brief can destroy a production batch worth tens of millions of dollars. Water is the third requirement, not city water. Ultra-pure water produced by an on-site treatment system that strips out every dissolved mineral, trace metal, bacterium and organic compound down to concentrations measured in parts per trillion. The water consumption across rinsing, etch and deposition processes runs into millions of gallons every single day. Producing and treating that volume requires a dedicated on-site facility that rivals a small municipal water treatment plant in complexity. The land preparation phase alone, the electrical substation, the water systems, the access infrastructure, and the initial earthwork can run several $100 million before the first structural concrete is poured. Then you build the shell. The structural envelope of a leading edge fab is engineered to aerospace tolerances, not commercial building standards. The foundation uses deep concrete piles, seismic isolation systems, and vibration damping elements that are custom designed for each specific site. The manufacturing floor slabs are reinforced concrete, often 4 to 5 feet thick, built to carry equipment loads of hundreds of tons per bay without any measurable deflection. The building itself requires miles of specialized piping for process gases, chemical delivery systems, and exhaust handling systems that don't appear in any standard commercial construction specification. Shell construction, from breaking ground to a finished enclosed structure, takes 12 to 18 months under favorable condition. Then comes the clean room, which is where most people's mental model of manufacturing breaks down entirely. Inside the finished structural shell, you construct an entirely separate controlled atmospheric environment, its own pressurization systems, maintaining positive pressure to prevent contaminated outside air from entering. The air handling unit cycle filtered air in laminar flow, smooth, unidirectional airflow that systematically sweeps particles away from critical surfaces rather than allowing them to drift randomly through the space. Its own ULPA filtration, which captures airborne particles down to 0.12 micron. A continuous environmental monitoring network tracks temperature, humidity, particle counts, and airborne molecular contaminants across hundreds of independent zones simultaneously. At the most critical process areas, the lithography bays where chip patterns are burned into silicon, the required cleanliness standard is ISO Class 1. A hospital operating room, considered one of the cleanest environments in ordinary human life, runs at roughly ISO Class 5. A chip fab at leading edge production is approximately 10,000 times cleaner than that by particle count. A single human hair in the wrong zone would contaminate an entire production bay and destroy every wafer being processed at that moment. Workers inside the clean room wear full body bunny suits, sealed cleanroom garments covering everything, not to protect themselves from the manufacturing environment, but to protect the manufacturing environment from them. Cleanroom commissioning. Getting from a finished structural shell to a fully qualified production, ready clean environment takes 9 to 12 months. And when that process is complete, you still don't have a factory. You have an expensive, very clean, empty box. Now the equipment. There is one company in the world that manufactures the lithography machines used in leading-edge semiconductor production. One. It's ASML, a Dutch company headquartered in Eindhoven, Netherlands, and it holds a complete, unchallenged monopoly on extreme ultraviolet lithography technology. No other company has commercialized an EUV system. No credible competitor is close. These machines project light at a wavelength of 13.5 nanometers, far shorter than visible light, generated by firing a powerful laser at tiny droplets of tin to produce plasma, and use that light to print circuit patterns onto silicon wafers coated in photosensitive material at a precision that approaches the limits of what the laws of physics permit. A standard EUV scanner from ASML costs approximately $180 million. ASML's newest high-NA EUV systems, which achieve finer resolution than the standard models and enable the production of today's most advanced chips, cost between $350 million and $400 million each per machine. Transporting a single EUV system from ASML's facilities in the Netherlands to a customer's fab requires 3 cargo aircraft, 20 trucks, and 40 shipping containers. Each machine contains over 100,000 individual components, approximately 2 kilometers of cabling. After delivery, installation inside the clean room, and calibration to production, ready specifications take several additional months. ASML produces fewer than 60 EUV machines per year globally, and demand has consistently exceeded that output. Before you can even order the machines you need, you have to qualify as an ASML customer and wait in an allocation queue that already contains every major chip manufacturer in the world. A fully operational leading-edge fab at the 3-nanometer node requires dozens of EUV scanners, plus hundreds of additional specialized tools, ion implanters, chemical vapor deposition chambers, atomic layer deposition systems, plasma etch tools, chemical mechanical polishing machines, metrology instruments capable of measuring features invisible to any conventional optical system. Each of those tools costs between $5 million and $50 million individually. The total equipment capital expenditure for a single competitive leading-edge fabrication facility, $10 billion to $15 billion. Equipment alone. That number doesn't include the building, the land, the utility infrastructure, the clean room fit-out. TSMC's Fab 18 in Tainan, Taiwan, the complex where the majority of the world's most advanced AI chips are produced today, spans approximately 1/3 acres and is built for a monthly production capacity of 200,000 12-inch wafers at advanced nodes. Its construction cost was estimated at approximately $19.6 billion. When TSMC announced its Phoenix, Arizona facility in 2020, the announced investment was $12 billion. By 2024, that number had grown to $65 billion for 3 fabs. By 2025, the total Phoenix commitment stood at $165 billion. By mid-2026, still under active construction, the number had reached $265 billion, covering 10 wafer fabs and 2 advanced packaging facilities. For reference, the annual gross domestic product of New Zealand is roughly $250 billion. Now, once the building exists, what does operating it cost? Electricity is the first and most relentless line item. A large advanced fab draws between 100 and 200 megawatts of power continuously, around the clock, every day of the year. Annual electricity costs for a facility at the 3-nanometer node run from $100 million to $300 million per year, depending on location, local energy rates, and facility efficiency. Materials are the second major category. Every wafer moving through an advanced fab consumes silicon substrate, specialty process gases, photoresist chemicals, developer solutions, chemical mechanical polishing compounds, and hundreds of ultra-pure compounds used in deposition and etch steps that build the chip layer by layer, 1 nanometer at a time. A small number of companies globally manufacture semiconductor-grade photoresists to the purity required for EUV lithography, and the silicon wafer supply itself is dominated by a handful of producers, meaning the supply chain bottlenecks don't end with ASML. Materials costs account for 35 to 45% of total operating expenses at a leading-edge facility. At the 3-nanometer node, chemical material costs alone run approximately $2,000 per wafer process. Labor is the third category, and the one most systematically underestimated. A full-scale advanced fab requires thousands of employees, but not general manufacturing workers. Process engineers with years of experience on specific tool types. Equipment technicians trained to maintain systems that cost more than most companies are worth. Facilities engineers who operate the ultra-pure water systems, specialty gas delivery infrastructure, and vibration control systems. Shift supervisors coordinating production across a facility that runs 24 hours a day, 365 days a year, because you cannot turn a leading-edge fab off. The capital intensity of the equipment means that every hour of idle time is capital cost burning without output. Training a process engineer for a new leading-edge node takes years, not months. The knowledge required isn't fully captured in training manuals. It lives inside people who have operated these specific systems through an entire generation of process development. TSMC's Phoenix project is expected to create approximately 6,000 direct manufacturing jobs. It took years to begin filling those roles at scale because the specialized expertise was that scarce globally. Now the number that business plans consistently underweight yield. A wafer starts as a perfect silicon disk, 300 millimeters across. By the time it completes an advanced manufacturing process, after 600 to 1,000 individual processing steps at the most demanding nodes, some percentage of the chips etched onto it will have failed. A stray particle of contamination in the cleanroom, a microscopic defect in the photomask used to project the circuit pattern, a deposition step that results in a film a few atomic layers too thick. Any of these errors kills the chip it touches. When a new process node enters production for the first time, our yield rates commonly run below 50%. Commercial viability requires yields in the 70 to 80% range. World-class mature production on a node that has been running for a year or more achieves 90% or above. But even at 90% yield, which represents genuinely excellent manufacturing, one chip in every 10 coming off the line is garbage. On a 3-nanometer wafer costing approximately $19,500 to process, a 10% failure rate means you're discarding nearly $2,000 of processed silicon per wafer before selling a single chip. At a fab running 200,000 wafers per month, even a small shift in yield has consequences that reach into the hundreds of millions of dollars. A single percentage point of yield improvement at scale is worth more annually than the entire revenue of most industrial companies. This is why yield engineering is its own department, its own career, its own existential priority inside every fab that operates at the leading edge. A bad yield quarter doesn't mean compressed margin. It means you spent billions in fixed costs and produced a fraction of the output required to cover them. How does any of this get financed? The actual capital structure for a leading edge fab involves several layers. The parent company's accumulated equity, typically built from decades of profit on prior technology generations. Long-term customer commitments, not just purchase orders, but multi-year supply agreements, often with prepayments, in which major customers commit to buying capacity from a facility that hasn't been built yet, because without that revenue certainty no bank will underwrite the construction financing. And government subsidy, which has become increasingly central to the economics of building outside of Taiwan. The US CHIPS and Science Act, enacted in 2022, allocated $52 billion to stimulate semiconductor manufacturing on American soil. TSMC's Phoenix project received up to $6.6 billion in direct federal grants and approximately $5 billion in federal loans under the program. Intel's US expansion received $8.5 billion in CARES Act funding. Samsung received $6.4 billion. And yet, $6.6 billion represents less than 5% of TSMC's total planned US investment. The government money matters, but it is not what makes the factory financially viable. What makes it viable is that every major technology company in the world needs TSMC's capacity, and TSMC has leveraged that position for decades to fund construction that would otherwise be economically impossible outside of Taiwan. TSMC's total capital expenditures in 2024 were approximately $29.76 billion in a single year. In 2026, the company guided to capital spending of $60 to $64 billion for that year alone. So why do only 3 companies, TSMC, Samsung, and Intel, operate at the leading edge, and why does TSMC control roughly 90% of that market? The answer economists reach for is barriers to entry, and that's accurate. But it doesn't go deep enough. It's a knowledge problem as much as a capital one. Every advanced process node that has ever been successfully manufactured required solving thousands of problems that had never been solved before. Process chemistry problems, contamination problems, lithography optimization problems, yield problems unique to that specific combination of materials, geometries, and equipment configurations. The solutions to those problems live inside engineering documentation, inside institutional memory, inside the accumulated judgment of engineers who spent years on specific toolsets at specific companies. When you build a fab from scratch, you inherit the equipment. You do not inherit any of that knowledge. You spend years learning, at enormous cost, all the lessons your competitors absorbed on cheaper, older technology 2 decades earlier. Intel is the most instructive example in the public record. Intel has been operating semiconductor fabs for more than 50 years. And in 2019 and 2020, Intel could not successfully ramp its 10-nanometer process at competitive yield, a node TSMC had already been shipping to commercial customers. Delays, more delays, a full restructuring of the process roadmap. A company with more fab experience than almost any organization on Earth still couldn't compress the knowledge curve fast enough. The lesson is that even Intel, with 50 years of institutional memory, still found the leading edge knowledge problem this hard. TSMC has approximately 90% of the market for the most advanced semiconductor process nodes. Samsung has most of the remaining 10%. Every Nvidia GPU training an AI model, every Apple processor in a smartphone, every AMD chip in a cloud data center, at the leading edge, all of it flows through this duopoly. If Fab 18 in Tainan experienced a major operational disruption tomorrow, the global AI infrastructure buildout would not slow down. It would stop. There is no comparable backup at scale anywhere in the world. The most consequential manufacturing supply chain on Earth runs through a 103-acre complex in southern Taiwan, built over 40 years by a company that has compounded its advantages to the point of being structurally irreplaceable. So here is the actual verdict. To build a single competitive leading edge fab today, you need $20 to $40 billion in initial capital. Toward the higher end if you're building outside of Taiwan and paying the labor and logistics premium that entails. 5 years pass before your first wafer ships. An allocation from ASML must be secured. The company produces fewer than 60 EUV systems per year for the entire global industry. Anchor customers must commit to purchasing capacity years before the facility opens, willing to pay for chips that don't exist yet. Government co-investment of billions is effectively required, because without that support the economics outside Taiwan don't close. And then, even after all of that, you would be competing against an organization with 40 years of accumulated process knowledge, 90% market share, gross margins that fund continuous reinvestment, and a customer list that includes every major technology company in the world. The financial barrier is real, but it's not the deepest one. The deepest barrier is the 40 years. TSMC started accumulating its knowledge base in 1987. The chips powering today's AI systems are the direct consequence of decisions made before most of the engineers building those AI systems were born. Any competitor starting today is beginning that accumulation now. A single fabrication plant costs more to build than most companies are worth. But the cost of building one is not what makes this industry what it is. What makes it what it is the 4 decades of compounded knowledge sitting inside the building once it's done. That's the part that doesn't appear on any balance sheet, and that's the part that can't be built in 5 years, no matter how large the check.